Hello and welcome to the third lecture of the course Analog Integrated Circuits. In this lecture, we are going to study about the active load connected to a MOSFET and what are its advantages and issues. Let's quickly revise the common source amplifier with a passive load, that is a drain resistance is present which acts as a load, and the amplifier gain, as we know, is equals to minus gm times rd. So how can we increase the gain of this amplifier? We can increase the gain of the amplifier by either increasing gm or by increasing rd. Gm, the transconductance, can be increased by increasing the gate bias voltage, that is vgs minus vt, the overdrive voltage, since gm transconductance is directly proportional to vgs minus vt. However, VGS minus VT actually defines the lower limit of the drain voltage that is possible to be achieved during the saturation mode. So if we increase the gate bias voltage, it means that we are increasing the lower limit of the drain voltage, and hence the output voltage swing at the drain would decrease. Another way could be is to increase the size of the transistor, since the transconductance is a factor of the size of the transistor W by L ratio. So this is one possibility. And in MOSFET, especially when we are talking about integrated circuit application, integrated circuits design of a current source, this is well a possibility. However, it has its own issues because it's not always possible to increase the size of the transistors indefinitely. You will be occupying more chip real estate. So the other way could be is to increase the drain resistance, and this drain resistance, if you talk about integrated circuits, it's very difficult to implement the big value of drain resistance on an IC, because the technology of the IC is geared towards the fabrication of better and better transistors. So the are difficult to integrate on an IC, and their tolerance is also very high. So that's why we cannot create reliable resistors on an IC. Also, by increasing the RD, the drain voltage would decrease, and a drain voltage decrease would mean that the output voltage swing would be lower. So that's why the common source amplifier with passive load is not very much recommended on an IC implementation. Next, we will see how we can circumvent this problem. Now let's consider an transistor with an active load, and the active load is actually an active device such as a diode or a transistor. So as a first example, we are going to study about the diode connected transistor, and this is basically a legacy name from the times of BJT. So in a BJT, if you connect the collector and base together, then what happens is that the equation of the BJT, that is IC is equals to ISE to the power VB over VT. Since collector and base are the same, it means that the collector current is now a function of the collector voltage, just like the diode current is a function of diode voltage. And effectively, a BJT becomes a diode between the terminals collector and emitter. And this is its small signal model. If we see the small signal model of a BJT, and if you look at it from between the collector and emitter, then it appears as a resistor. What you see is actually a resistor between the terminal collector and emitter. You might be wondering, no, there is also a current source present. But if you see the current source, the voltage dependent current source, the current from this path is a function of the base to emitter voltage. What is the and if you talk about a resistor, the current through a resistor is also a function of the voltage. Then how can you differentiate between a resistor and a voltage and a current source, may I say? So actually, when we talk about a resistor, the current through a resistor is a function of its own voltage. Whereas when we talk about a voltage dependent current source, then the current through this component, that is the current source, the current through the current source is a function of a voltage at some other place in the circuit. For instance, we know GMVB, but in this particular case, we see that the voltage across the current source and the voltage at that other place, that is VBE. So since VBE is equals to VCE, it means that the current through the current source is a function of its own voltage. Hence, this current voltage dependent current source is effectively a resistor as well. What would be its resistor? Its resistance would be 1 over Gm. So hence, the terminal between the terminal emitter and collector, this would appear as a resistor. In the same way, we see the MOSFET. Here we have connected the collector, the gate and the drain. So it's not really a diode, just like a BJT, but it carries the same name, that is the diode connected transistor. It's not really a diode because you see there is no exponential relationship between the current and the voltage here. At best, there is a square law relation. So if we see its small signal model, it would appear like this. So in FET, Vg is equals to Vd. And this means that the transistor would always remain in saturation, just like in the BJT, the transistor would have always remained in active mode. Also, the small signal resistance, if you talk about the small signal resistance model, likewise, between the source and the drain, the transistor would appear as a resistor. Can you guess what would be the resistance between the drain and the source? I've already explained an analogy with the BJT world. So what is the resistor looking into the MOSFET from source? The MOSFET from source, what is going to be the resistance here? Any idea? Yes, it's going to be 1 over Gm. This is going to be the resistance here. So that is about the diode connected transistor. Now next we are going to connect this diode connected transistor with an amplifier stage and see what happens. Now suppose we have this configuration here and we have connected a diode connected transistor at the drain of this common source. Again, the biasing at the input is not shown, but you can well understand. So about the diode connected transistor, one thing is that we should be able to make the small signal models rather quickly. And if we look at this circuit, the small signal model goes like this. And the DC side is grounded. We are going to connect the gate and the drain together, and the source is connected down to the drain of the transistor, which is lower end, and then here we have the input. The source of the lower transistor is grounded. So this is the input voltage, and for this, let's say we have GM1 and VN, I would say. This is the gate, the drain, and the source. Now about here we have the source, the gate which is connected to the drain and which is grounded. And for this transistor, we have this is GM2 VGS, and if we look at VGS, so that would be equal to minus GM VS2. So this is the small signal circuit. For this, the big question is, what is the input resistance seen from here? So what is this resistance which is looking inside the circuit? And if we see how can we find the resistance looking into a circuit? So let's see how do we do this thing. So it is like, if you see, it's actually a voltage dependent current source whose other end is grounded, and the magnitude of this source is GM2 rather minus GM2 VS2. because the gate is grounded as well. You can see it here. This is the gate which is grounded since it is connected to the drain. So it means that VGS2 would actually be minus VS2. And if we want to see what is the impedance of the circuit, the standard method says that we introduce a voltage source from our own end, let's call it Vx, and try to find out the current which goes into the circuit, may I call it Ix. So now R would be equal to Vx divided by Ix. So if we look into this circuit, what is the current which is going inside? So it means that we see that Ix and this. So it means that Ix is in fact equals to minus of the current of this current source. And what is the current of this current source? It is minus GM2 VH2. So this would mean that Ix is equals to GM2 VS2. So this is Ix equals to. And incidentally, since we know that this point is in fact the source, so if you see, in fact, this is the voltage which is Vs2, because what is Vs2? Vs2 is the voltage at the second source of the second transistor. Just for the understanding, I can say that this is transistor number 1, and may I say this is transistor number 2 and 2. So Ix is equals to Gm2 Vs2. Therefore, I can say that R is equals to Vs over Ix. I'm showing each and every step, and that's why it's going to take a bit of time. That's Vx over Ix, and this is hence equals to 1 over Gm2. So we can say that the resistance which is looking into the second transistor is in fact equals to 1 upon Gm2. And from the common source, we know that the gain of the circuit is in fact V0 over Vn, because this is the point where we say we take out the V out. So V out over Vn is equals to what? So V out upon Vn is equals to minus Gm1, that is the gain of this circuit, multiplied whatever is the resistance present at the drain of the transistor. So at the drain of the transistor, we see that the resistance we have is in fact equals to 1 over Gm2. Therefore, we can say that the total gain of the circuit is minus Gm1 over Gm2. So, as we used to practice on boards as well, V out over Vn is equals to minus Gm1 over Gm2. This is the gain of the circuit. And now we can think about what is going to be Gm2. Is it going to be a big number? Is it going to be a smaller number? And if Gm2 is small, we are going to have a bigger gain, etc. So this is basically the equation. And now we see how useful it can be for us. For instance, if we look at it now, so it is a ratio between the two transconductances. So how can we represent the two transconductances? We can see that the two transconductances are in fact we can represent the GM. If we look at GM, then GM is equals to, let me show you a minute. So GM as we know it is equals to $2ID over VGS minus VT. And we know that ID is equal to half mu n Cx W by L VGS minus VT the whole square. So if we look at GM1 over GM2 and substitute the respective values of ID and VGS into it, what we will get is in terms of ID and I1, which would be equal to, I would say, goes like this, that it is going to be 2 mu n COX W by L. And if we're talking about first transistor, that's going to be W by L of 1 times ID of 1 divided by 2 times mu n COX W by L of 2 ID of 2. How did we do it? We simply replace the value of VGS minus VT in terms of ID in the equation using the relation of saturation current, and we get this. And since we are talking about integrated circuits, so these two transistors would share the same mobility, will have the same capacitance per unit area. So what we see is that the mu n and this thing, it gets cancelled, and you see whatever is the current from one transistor would go into the other. So we can see that even the currents are the same. So hence what we see here is that GM1 over GM2 is going to be square root of W by L of 1 divided by W by L of 2. That is, the transconductance ratio is in fact the sizing ratio of the two transistors, which means that let's say we want to have a gain of 1. So if we want to have a gain of 1, a gain of 10, it means that the W by L ratio of transistor 1 and transistor 2 should have a ratio of 100. Or in other words, this transistor, which is the main transistor, is going to be 100 times the size of this smaller transistor. So this transistor M2, the diode connected load, is going to be a small transistor, whereas this M1 is going to be a much bigger transistor. So by looking at the circuit, you can guess that the gain of the transistor, which is minus GM1 over GM2, is a function of the device dimensions, and it is independent of the biasing of the circuit. It becomes independent of the biasing of the circuit. Regardless of the biasing of the circuit, the gain of the circuit is fairly constant. So if are any variations in the biasing of the circuit, it is not going to largely affect the circuit, which is a big boom. However, there is more than what meets the eye. I have done a very simplified, rather oversimplified small signal modeling of the circuit. Why do I say this? For instance, when we are looking at the circuit and it is a diode connected transistor and its source is not grounded. So when the source of a transistor is not grounded, rather the bulb and the source of the circuit are not connected together. Please remember that this bulb of the circuit is tied up usually with the ground. And here, since the source is not grounded, therefore the substrate effect comes into play. For substrate effect, how does it affect the circuit's performance? Because the substrate effect is actually like a backgate effect. So it is modeled as another voltage dependent current source in the circuit. So here I'm going to now make the version of this circuit which is more accurate. And how would it appear? Let's see this. now we try to make it also the model which is more accurate. Then the gate and the drain are still short circuited. The drain is connected to the ground. There is a voltage dependent current source, and then there is another voltage dependent current source between the drain and the source. And this one we knew it is GM2 VGS2. This one we call it GMB VBS. So we have included both of these effects. And if we want to make it even more accurate, it is possible to include the channel length modulation effect, and we can include R0. But it is, it goes like that. Most of the time, R0 is optional, but GMB VBS, that is the substrate effect, is sort of mandatory. Whenever you are using a transistor and not connecting the source terminal to the ground, we must include the substrate effect. So if we do this and now we change the circuit, so we would see that the lower transistor circuit that would remain the same. It is the GM1, and this is going to be GM1 VN, and this is in fact VN, and from here we take V out. So now the question remains, what is going to be the voltage, the resistance seen from here at the upwards direction? And again, I believe that just by the analogy, you can see that we can say R is equals to, earlier it was 1 over GM2. Now there is GM2, and you can say it is now in parallel with 1 over GMB. So it's like two conductances which are in parallel. So we know that the conductances, when they are in parallel, they actually add up. So we can say that R is equals to 1 upon GM2 plus GMB. Therefore, the output to input equation would change a bit and would now be equals to minus GM1 over GM2 plus GMB. This can be changed into its form, and we can represent it as, you may say, to make it comparable to what we have done earlier, GM1 GM2 times 1 upon 1 plus eta. And what is eta? That you can understand, I believe, that eta is equals to the transconductance due to substrate, the ratio of this to the transconductance of the diode connected transistor. So this is a definition, and we see that minus GM1 upon GM2 is equals to this. And let me tell you that the transconductance due to the substrate effect is a very small number. For all practical purposes, we can even ignore it, and then we would still have the same ratio, which is equals to V out over Vn is equals to minus GM1 over GM2. And this is the effect of the substrate on the design. So this is how we can have the circuit, and using a diode connected transistor, we have seen how it can be used. Another issue with this circuit would be that we have seen the substrate effect. One way of mitigating this effect is to use a PMOS transistor. We can use a PMOS transistor. What would be the advantage? Well, the advantage would be, since we're using this, I'm sorry. So we have now this circuit, and in here we apply the input. So without going into again the small signal model and everything, now since the source is connected to VDD, the bulb is also connected to VDD, we don't have the substrate effect. What will be the resistance when we look at the circuit from here from the drain side? What is it going to be? So again, since the collector and drain they are connected together, this resistance is actually going to be 1 over GM2. So R is equal to 1 over GM2. Let's call this transistor N2 and this one as N1. And what is going to be the output upon input for this circuit? So again, that's going to be minus GM1 over GM2. Again, if we substitute the values of GM1 and GM2, what would be the result? There is going to be a change, and that is mu n COX W by L of 1 times ID1 divided by everything is in the square root, and of course mu P COX W by L of 2 ID2. So the two transistors are still in series, means that the current would be the same, they can be cancelled. COX are the same, capacitance per unit area, it can be cancelled, but mu n upon mu p, they cannot be simply cancelled because the mu n, the mobility of the electrons and the holes are not equal. In fact, mu n is greater than mu p. And usually, as a rule of thumb, we can say is that mu n is roughly equals to twice of mu p. So what we see here is that V out upon Vn is equals to, you can say, twice of W by L of 1 divided by W by L of 2. So you see, now the width to length ratio, the W by L1 and W by L2, we see that if we want a gain of, let's say, 100, then the W by L ratio would be only 50. Or earlier it was 100. So the disparity between the sizes of the two transistors, because just imagine if we have two transistors in a configuration and one transistor is about 100 times the size of the other, it would be very difficult to place them properly. So that becomes the layout. The placement of the transistor is actually called the layout issue. And that's why if we use a PMOS transistor, that would be a better decision, because we can have actually the transistors which are somewhat smaller in size, and we can still achieve the same gain. So that is why we use this mu n over mu p, the mobility difference for the gain. Okay. So I hope it is a bit clear. Now there is a downside of using this PMOS. What is the downside? Let's look at it. So let's compare the current of the two transistors. We know that the current for the two transistors would be the same. So we can say that ID1 is equals to ID2. If we put the equation of the two currents here, so half mu n COX W by L of VGS1 minus VT the whole square equals to half mu T COX W by L VSG minus VT the whole square. So here half is cancelled, COX is cancelled. This is, by the way, W by L of 1, this is the W by L of 2. So what we see here is that we can have the same factor, uh, which is mu n W by L of 1 divided by mu p W by L of 2 in a square root way, and this would be equal to VSG2 minus VT over VGS1 minus VT. Therefore, we can say that V out upon V in is equals to VSG2 minus VT divided by VGS1 minus VT. Now let's just pause for a minute and see what we are saying. We are saying that the voltage gain, is in fact a ratio between the overdrive voltages of the two transistors, N1 and N2, these two transistors. This is one thing. Secondly, whatever ratio that we obtain, that can be obtained by adjusting the overdrive voltages. So let's say the same value, we are a gain of 10. So to attain a gain of 10, the ratio between these two overdrive voltages would be also 10. So VGS1 minus VT is for M1, the transistor, the main transistor, and we keep VGS1 very small, so keep it deep into saturation. So let's say VGS1 minus VT is a small number. Let's say it is 0.2. If it is 0.2, you can see if it is 0.2 and we are targeting something like uh, 10, a gain of 10, then it means that VSG minus VT is equals to 20. I'm sorry, 2. So let VGS1 minus VT, the biasing of the common source transistor, is equals to 0.2, which implies that VSG2 minus VT is equals to 2 volts. Usually threshold voltage is low, and even if you assume something like 0.7 volts, so it's a fairly practical value. It means that VSG2 is equals to 2.7 volts. So we are talking about the N2 transistor, and this means that the source potential minus the gate potential is equals to 2.7 volts. So what about the gate potential? VG2 is equals to VDD minus 2.7 volts, since Vs is equals to VDD. So VG2 is equals to VDD minus 2.7, and it's a diode connected transistor, which means that VG2 is in fact equals to VD2. Therefore, VD2, the minimum value of VD2 is VDD minus 2.7 volts. So this is the kind of value that we have. This is the voltage headroom. So the upper transistor is consuming about 2.7 volts. So we are applying this supply of VDD volts and the potential at the drain, because VDD2 and VDD1 are the same. VDD1 is equals to VDD2. We are talking about the same node. So it means that the voltage headroom is fairly large. If we use, now we see that if we use a diode connected transistor, what is that we obtain? We are obtaining a gain which is equals to GM1 over GM2, and it is fairly independent of the bias point. It depends upon the device dimensions. If we use a diode connected transistor comprising of an NMOS transistor, then that transistor would mean that the device mismatch, or I'm sorry, the device size difference would be fairly large. If you use a PMOS transistor, the device dimension mismatch would be half of that. Moreover, with the common source transistor and an NMOS based connected diode, we would have a gain which would be GM1 over GM2, but at the same time there will be substrate effect. PMOS does not produce any substrate effect, but we see that the voltage headroom is the price that we pay. So this is about using a a diode connected transistor with a circuit. What else can we do? We have seen earlier current sources where the diode connected transistors, they are used, and instead of using a diode connected transistor, we can use a current mirror, because current mirror is yet another active element. So in the next session, we would see what would happen when we would use a current mirror as a load. So I hope you have followed it. If there are any discrepancies, if there are any questions, I would be very glad to answer it in the live session. And these things are not trivial. It takes a lot of effort to assimilate it. I understand this, but once you get the hang of it, then it becomes not so difficult. The book that I am following is Razavi. You can find this topic in Razavi as well, and this is, I think, in chapter number 3, the topic that I've been presenting. And let me tell you, I've really diluted it for you. So that is from page number 53 onwards on Ravi's second edition. So do have a look at the book as well, and you will see it for yourself. So that's all for now. Thank you very much for listening.